The following is the chapter concerning with the potential flow and rock and leaf forks, created during the 19 COVID period. If there is some missing or not good, so I'm sorry about that. Now we come to the main portion, please. Okay, now we come to a method for studying plant potential flows through stimuli and potential function. The problem in this chapter we divide in two cases. The first case is given the potential function phi or stream function psi. Determine the velocity field of the flow. You yield the relationship between the velocity field Ux Uy with respect phi and psi. Okay, phi and psi, and you can if given this first, then you yield the differentiation, we can get the result. This is type of derivation problem hang on the formula, the formula, you see, this formula for psi, or this formula in the polar coordinate for psi, and this formula for Cartesian coordinate system, or we use this one for polar coordinate system. Okay, and we take the derivation phi or psi with respect x, y, or r theta. You can get Ux, Ey, or Er, U theta. To find the pressure at any point in the flow field, we use the Bernoulli equation applied to unknown point and a given point be 0, U0, usually the point at the boundary. I show you the Bernoulli equation. This is a Bernoulli equation. E constant at any point on the flow field. Then you apply this one for 2 points. One point unknown, the value of pressure have the velocity, but another point B0 given normally at the boundary. So you apply this equation for 2 points, you can solve for the pressure at any point in the flow field. And using the method of integral, we can find the force due to the flow acting on a certain section of surface based on the pressure found in the previous step. This step, It should be noted that the properties of hydrodynamic pressure are perpendicular to the surface for the ideal fluid flow without viscous friction, because we consider about the ideal fluid flow. Therefore, the hydrodynamic pressure are perpendicular to normal to the surface. And the fourth point, find the flow rate through a curved section. In fact, the curved area created by the straight line perpendicular to the x or y plane, having a thickness of 1 meter, slipping along the curved segment, connect to 2 points A and B. We apply this formula, we can find the discharge or flow rate. I show you this formula. You use this formula to calculate the discharge passing through any curve connect to 2 points A and B by you find the streamline stream function psi, and you calculate psi B and psi A by replace the coordinates of A and B into psi function, and after that you use this expression to find the discharge. Okay. The second kind of the problem give the velocity field. It is required to find the potential function phi or stream function psi. In this case, the velocity field given first. You have to find the phi and psi. Okay. So in this type of integral, this type is a kind of integral problem, namely solving the Laplace differential equation. So you see, you use this one, this one we call the Laplace equation for a streamline. Okay, you integral this one, you can find psi. Okay, or you use this one. This is also Laplace equation for phi function. Okay. The two integral constant will be specified based on the extremely for condition and boundary condition. So we use two kinds of condition. Boundary condition. Extremely far condition. That means at a point very far from the region studied. At that point, the velocity and the pressure are given. So you apply the condition at that point. Boundary condition. So we have two kinds. The first kind, psi constant. Psi constant, you remember psi constant is a streamline, and the derivative phi with respect n equal 0. This one that means the velocity normal to the boundary, or the velocity n un along n, the velocity un equal 0. That means the flow cannot move inside the boundary. Okay. And now very important method of superposition. Since the potential function phi and stream function psi is derived by the linear partial differential equation, Laplace equation, so we can compile many single simplified potential flow into a complex potential flow, synthesizing many plane potential flow, or analyze a complex flow into more simple potential flow. That is called the superposition method. Okay. This can be ruled by we call phi 1 and phi 2 are two potential functions, because both satisfy the Laplace equation, so we can write the first and the second like this. Okay, and now we sum side by side. Okay, and we get this one, and now we let phi equal phi 1 plus phi 2, and so here we have the second derivative with respect x, and plus this one phi also. So you can see this equation is also Laplace equation. Now we come to the basic plane potential flow based on this method. So the very important is we have to know, to study about the basics basics potential flow. Here, basics plane potential flow. The first one, uniform flow. We have the velocity u made with x an angle alpha. So from this one you can find ux equal u cos alpha, and uy equal u sin alpha, and you can put in the in this equation. You can put in this equation, because you know this one and you know this one. You put here and you take the integral, you can get size, or you put in this equation. Ux no, uy known. This is direct for a plane potential flow. So you integral, you can get this one. You can use this one. Here you can use this equation. Ux known, uy known. Ux is equal u cos alpha, uy equal u sin alpha. You put here and you take the integral, you get phi. Okay. Okay. Finally, you get phi in Cartesian coordinate system like this. Ux, uy constant. Ux, you know Ux equal u cos alpha. Uy equal u sin alpha. Put here, you get the functions psi in the Cartesian coordinate system, and in the polar coordinate system we have this one. You have this one. And for 5 function in Cartesian coordinate system and a polar coordinate system, we have 2 equations, this equation and this equation. And this figure show you the streamline. No, this streamline is concerning about the source and sink. Now we consider about source and sink here. Now we assume the source or sink at origin O. Okay, so you can know that source point is a point in the flow field at which there is a fluid source with constant flow rate equally pouring in all directions. That means at the point we have the flow field out on the side around this point with a constant flow rate. So, and the sink point or section point or well, in contrast to the source point, is a point in the flow field at which the fluid is removed with a constant flow rate. That means the fluid around this point move to this point with a constant discharge, and the source or sink point stand is the volumetric discharge of the source or sink per unit thickness. The intensity of the source point is positive. Now you know source point, the value is positive value, and the sink point the value is negative, but the intensity the same. Okay, but different the sign. For source point the sign is plus, for negative. For sink point the sign is minus. The flow velocity passed through the source point component of normal velocity to straight line connecting center of source is 0. So you can for the source or the sink, the velocity u theta equal 0, because you see here the flow just from this point outside, direction outside, or go inside to this point. Therefore the velocity normal to this line is 0. So that means the velocity just er and u theta is 0 here. So you can put in the formula to find psi by integral. You can get psi for polar coordinate system, or you change into the Cartesian coordinate system. By theta you change arctan y over x. And similarly we can find phi equal q divided by 2 by log r, and if we substitute r by x square plus y square power 1/2, and we put 1/2 outside this one, we get q over 4 by, and we get this one in Cartesian coordinate system. So now you remember, if you put positive before Q, we get the short bond. And if we put minus before Q, we have sinh bond. And at a point, any point, M0, X0, Y0, that means the short or the sinh at this point, not at the origin, but this one. So you can use the method to move the coordinate system X or Y to the origin M0. So you can write phi and psi like this: psi plus or minus Q over 2 by arctan. This one become Y minus Y0 divided by X minus X0. And for this one, we use this formula. This one, X minus X0 power 2 plus Y minus Y0 power 2. Or you can delete the square root side and you put 1/2 out. That means you get Q over 4 by log X minus X0 power 2 plus Y minus Y0 power 2. Okay, you can cancel the square root side. So now we come to another kind, free vortex flow. Concept: the free vortex with a center at O is a flow such that the intensity gamma of the vortex along any enclosed curve around the center O once unchanged. So we have this formula to describe the free vortex flow. This one. That means we take the integral along the closed curve C, and this is enclose the point where the free force occur. Now we consider about the center O. That means we take any closed curve about the center O, and this is have to close curve, enclosed curve. So here C is a closed curve. Okay. A vector U, the velocity dot product with the dl a vector along the tangent line of the curve. So we take just one time, and we get this is constant. And gamma here is called intensity, and the value of gamma is positive if counterclockwise. That means here we take the integral on the curve, but in the counterclockwise the value of gamma greater than 0, and if lockwise then gamma less than 0 if lockwise. So the component of flow velocity passing through the center of vortex is 0. So you can see if we take a circle around the center O, this circle, then the velocity tangent to this circle, and the velocity normal to the circle. That means passing through the point O is 0. That means in this case, UR is 0 and U theta equal the value, this value divided by the length of the curve. The length of the curve 2 pi r. So then you can get the formula to calculate U theta equal this one, and UR 0. And then you can put in the formula to calculate, to integral the phi and psi. You get psi like this. In this is in polar, and this is in Cartesian coordinate system, and phi like this and like this for two kind of the Cartesian. And now we consider about the stream and the potential function of a vortex having a center at M. In this case, we consider about the center of the vortex at O. Now, if the center of the vortex at M, x0, y0, any location different from O, we can use this formula to calculate phi and psi like this in Cartesian coordinate system. So we can see the streamlines. In this case, the streamline are the concentric circle. The streamline are the concentric circle. Center on the vortex center. The equipotential lines. This one, the straight line passing through O, we call the potential line. Okay, potential line. The equipotential line are the straight lines passing through the vortex center. In this case at O, and orthogonal to the streamline, and the straight line passing through the point O, normal to the circle, the concentric circle at the center at O. Now we come to another kind of basic plane potential function, potential flow. Duplicate concept. Consider a synthetic flow created by a short bond and a sing bond based on the all axes symmetrically across a y-axis, separated by a segment of E, whose the intensity is Q. Applying the principle of superposition we have. Now you consider this is the x-axis, this is y-axis. If we have a point, a short point on the left hand side, on the left of the y-axis, and we have a sing point, okay, a sing point on a portion of axis, a positive of axis on the right hand side of y-axis, and short bond and sing bond we have symmetric through the y-axis, and the distance from short and sing point E. the distance E. Okay. Now we can write the flow by use the principle of superposition. We have psi equal to psi n. Psi n, that means psi of the source, and plus psi x. Psi x is side of sin. Okay, and we write the formula to calculate this one like this, and this one like this, and we can join together like this. Okay, for phi equal phi source and plus phi sin, we get this formula for this one, and this formula for this one. So we summation, we get this one, where theta n equal arctan y over y minus y0 divide x minus x0, but y0 is 0 because of this source and sin on the x-axis, therefore the y-axis 0. So we have this y, and x minus x0. x0 here on the left, so x0 is e over 2 minus e over 2 because on the left of the y-axis in negative. So therefore x minus x0 equal minus e over 2. Therefore we have x plus e over 2. And for theta of the sin, we have arctan y divided by x minus e2 because x0 here on the positive of the x-axis. So we have this one. And r equal square root of x minus x0 power 2. And because x0 here minus e2 plus y minus y0 power 2, but here y0 is 0, so we have the formula to calculate Rn. For R of the sin, Rx equal x minus x0 like this, because x0 equal e over 2, and y minus y0 power 2, and y0 equal 0. So the flow of the doublet is a flow created by a pair of source pole and sin pole distant apart by a segment E with a strand of Q such that E multiplied by Q approach to M0 when E approach 0, and M0 is called the doublet moment or intensity. Now from this one, the distance from the source to the sin, E the distance. Now you give E approach to 0, approach to 0. That means the source and the sin move approach to origin, and that means at point O, at the origin, we have two kinds of the flow. The first one, we have the source from the left move to O, and the sin from the right of the y-axis move to the O. Therefore at O we have two kinds, source and sin here. When we give the distance E from source and sin 0 to 0. So you can use the mathematics to find the limitation. And in this case we assume E multiply with the discharge, the Q, the value of the source or the sin. E multiplied by Q approach M0 when E approach 0, and M0 we call duplet moment or intensity of the duplet. Now you can see we can find stream and possession function of a duplet like this. This is for a Cartesian coordinate system, and this is for the polar coordinate system for phi, and for psi we have this one in Cartesian coordinate system. For this one in polar coordinate system. Comment. The streamline are the circles going through the origin. The streamline are circles going through the origin, whose center at on OY axis, and the equipotential line are circles that passing through the origin O, whose center lies on O axis and orthogonal to the streamline. So you see here. Okay, this is the streamline. R circle, and the center on the y-axis, and passing through all streamline. And for the possession line, it also a circle with the dashed line. Okay, a circle, and the center of the circle lies on x-axis for possession line, and all passing through all, and two family of circle, streamline and possession line, normal together. Okay, normal together, as you know. Now we come to the superposition of basic plane possession flow. The first one, the uniform flow around one source, the flow around half body. So in this case, the flow includes the first one is a uniform flow parallel to all x-axis. The direction from the left to the right with a velocity, a constant velocity of u from the left to the right, and u parallel to all x-axis. Okay, and we have a source located at the the origin, or we have a source whose intensity is Q. Now we use the superposition for two kind of flow, this flow. So we get the possession and the stream function like this, and you see phi here, and you multiply x if we find off the uniform flow, this one for uniform flow, and this one for source here, source and center of the source at O. You take this one sum with this one, yield the superposition method, so you get pi, and this is in Cartesian coordinate system, and we change into the polar coordinate system, we get this one, because this one is called R2, R power 2, and we take 2 outside, we can get this one become Q over 2 pi, and X, you know, we use you know that X equal R cos theta here, and for psi in Cartesian coordinate system, we like that, like this, and this one phi of the uniform flow, and this one psi for the source. So we sum 2 flow, we get this one, and we change into the polar coordinate system, we get this one. Very example, we just sum 2 component of potential flow, we get the superposition. Now this is uniform flow, you see, uniform flow, and this is source, and the center at all, we plus together, we use the superposition method, we plus together, we get this is the superposition of uniform flow and source here, okay, and this is the uniform flow around 1/2 body. In this case, we call it 1/2 body. That means we consider about the streamline have a phi equal Q over 2, and this streamline. And for this streamline, we see that this is we have a close here, but for on the right hand side, this is open, not close, open. Therefore, we call half body, close. This is open, half body, and I give you the stagnation point here. The stagnation point, that means the point where velocity is 0 here, and the distance from O to this point equal Q divided by 2 by U. So now we come to another kind of the superposition flow around the Rankine body. Flow around the Rankine body. That means the combination of uniform flow and a source and sink pair. I show you here. We have a source with the intensity Q source, and we have a sink also with the intensity Q source and sink symmetry with the y-axis, and the distance from source and sink to all are A, the same A here, and we have the uniform flow U parallel to the x-axis, flow from the left to the right, okay, and so now we get the combination of 3 kinds of flow, potential flow. We get this one. Synthetic flow includes the uniform flow U parallel to all x-axis, the direction from the left to the right, and the second, the source point is set at minus AO with an intensity of Q plus Q, because this is source. So this is plus. And sinh point is at AO, okay, with the intensity of minus Q, minus because this is sinh, okay. So we can find the potential and the stream function like this. This is phi, and this is psi in Cartesian coordinate system like this. And this is the graph. So this is we call a Rankine body. This is we call Rankine body, a closed curve. When we put psi equal 0, we can get this one, okay. Streamline when psi equal 0, we can find two k. The first one like y equal 0, so you can see here. When you put psi equal 0, you can find the streamline. And the first case, y0, this one 0, and y0, this one 0. So y equal 0, psi become 0. Therefore, the first case line equal 0, but outside of this curve. That means x-axis from minus infinity to a, and from b to infinity of x here the streamline. And the second case, if you put this one 0 and you solve this equation, we get this one, and this one is so the equation for the streamline when phi 0, and this equation so another. That means finally the streamline when phi 0 have a two portion. The first one on x-axis outside AB of this curve outside, and this curve also streamline, okay. And now we come to the stagnation bond and velocity at a specific bond. At A, B is the stagnation point. That means the velocity here and here is 0, okay. And for D and C, the velocity maximum, but the velocity on the velocity component is parallel to x-axis, and the component parallel to y-axis is 0. That means UCy equal UDy 0. Just have UDx and UCx and get the maximum value here. And for the stagnation point, I give you the formula to calculate this bond A and B by use this formula. You use plus for B and minus for A, okay. And now the Rankine body, we say something a little bit about the Rankine body. A closed curve C divides the flow field into distant parts. The first, the inner part, that means the part inside this curve, inside this curve, inner part, and the outer part, that means outside of this curve. These two parts do not have the reciprocal fluid exchange through C. That means the fluid not exchange from inside and outside, not. Okay, not exchange. The flow is like moving around the solid body covered by C. That means the flow at outside region go around this curve. This curve like a solid body, like a solid body, and this called as a Rankine body. So this one is called Rankine body. Okay. Now we come to another case. Uniform flow around a cylinder. We have a cylinder and we have a uniform flow go around a cylinder. And in this case, we divide in two cases. The first case is a fish cylinder. We have the concept for this flow. The uniform flow around a circle cylinder. A circle, you see, this is a circle cylinder. And this is you have a circle. A cross section of the cylinder is a circle, okay, and this is the uniform flow, okay. So the uniform flow around the circle cylinder is a flow around the Rankine body when I approach to 0, and you see this concept, you return to here, okay. This is a Rankine body. Now, if you move shock and sin together approach to O, this one move to O, and this one also move to O. That means I approach 0, and this one move to 0, become a doublet. You see here, the plate here become this one when the shock and sin move to O, become a doublet, okay. Therefore, uniform flow around a circle cylinder is a flow around a Rankine body, but Rankine body when I approach to 0, then the Rankine becomes into a circular cylinder. Now you can see here, when this one move to O and this one also move to O at the same time, then this one we call the Rankine body. In this case, Rankine body become a circle. This flow can also be viewed as a synthetic flow of the uniform flow and a doublet. You know, when shock and sin move to O at the same time, then this one become doublet. And we have a uniform flow and a doublet. That means the uniform flow around a circular cylinder similarly to the uniform flow and a doublet. Therefore, you can find the possession and stream function. Find like this for polar coordinate system, and psi like this for polar coordinate system. We have where R here, R is a radius of a cylinder, a radius of cylinder, and R equal m0 divided by 2 by u. M0 is called the moment of duplet, or the intensity of the duplet here. Here, when we have this one, m0 is called duplet moment, the moment of the duplet, or the intensity. And we have a comment here. The stimuli when phi equals 0. Now, if we put pi equals 0, we get the stimuli. In this case, we have two portions for phi equals 0. The first one, sine theta equals 0. We get sine equals 0. And sine theta equals 0, we get either phi equals 0, then we get this 0. That means the axis, the x-axis, and this one. But outside the circular, outside the cylinder, on x-axis, theta equals 0. Theta equals 0. We have sine theta 0 on the positive of the x-axis. This one, from b to infinity along the x-axis. And another, for sine theta equals 0, then we get theta equals by. That means this line on the x-axis from minus infinity to a, outside of the cylinder. So this line and this line is the stimuli. The stimuli when psi equals 0. And one more. If this one equals 0, this one also equals 0. So in the case, if this one equals 0, we can solve for r, small r, equal r. Small r equal r. Small r equal r. That means the second, this second. Okay? R equal r. The stimuli is C. C, this one. C. The circle with center at O, radius of R. The closed curve C divide the flow field in two regions, inside and outside. Inside and outside. The two regions do not exchange fluid to the curve C, and no exchange fluid between two regions, inside and outside, because we have the stimuli here, and no flow passing through the stimuli, as we know at the chapter 3. So the uniform flow is similar to that around a fish cylindrical body with radius of r. So in this case, if we consider this solid body, this is cylinder, solid cylinder. So we have the flow passing through a solid body is a cylinder. The velocity distribution on the surface of cylinder. Now we would like to find the velocity on the surface of the cylinder. We use the relation between the velocity and phi or psi. We can find the formula to calculate the velocity. U here, UR equal this one, U theta equal this one, and this one apply for upon outside of the cylinder. That means small r greater than r outside. And if r equal capital R, then we have upon on the surface of the cylinder. We put R equal R capital R. So this one 1 minus 1 equals 0, and in this case you are 0 on the surface of cylinder. You are 0. And when r small r equal capital R, this is 1 plus 1 2, and we get U theta equal minus 2 U sine theta. So on the surface of cylinder, the velocity U theta equal this one, and U r equal 0. Now we come to the distribution of the pressure on the surface of cylinder. Now we use the Bernoulli equation between upon on the surface of cylinder and upon at the very far region. So we write, after we write the Bernoulli equation and we manage the equation, we get delta B star equal B star minus B star at infinity equal rho U square divided by 2 multiply 1 minus 4 sine square theta, and the value of B star equal B plus gamma z. So with this formula you can find the value of the pressure on the surface of cylinder. If we assume this value is 0, if we use gauge pressure and this one 0, so we can find the pressure on the surface of the cylinder can be found by this formula. Okay, and now the second case, we come to the rotating cylinder. Concept: the uniform flow around the rotating cylinder can be conceived in 2 ways. The first one, combined flow, includes uniform flow, doublet, and free vortex. And the second, uniform flow around a fixed cylinder, and this one for this one, fixed cylinder. And after that, you plus with a free vortex. So you see here, in this case, we put more free vortex, then the flow passing through a fixed cylinder become the flow passing a rotating cylinder. We just add more free vortex. Here we assume that the free vortex flow is clockwise. That means the free vortex direction logwise. Okay, and if logwise, so by the convention, vortex intensity has a value of minus gamma, because the positive value is counterclockwise, and this is logwise. Therefore, we have to put minus gamma, with gamma positive. If positive, the potential and steam function. So finally, you can get the potential flow the potential function include this is the potential function for the uniform flow around the fish circular cylinder, this one, and we plus with this is the free vortex. You see this is minus because we put the vortex in the right direction vortex clockwise, and counterclockwise this is the positive value, but for the clockwise this is minus here, and here we can find psi. This portion, this term, describe the value of psi of the uniform flow passing through around the fish cylinder, and we plus with phi for the free vortex. This one we use positive because the direction of the vortex clockwise. So here R here, R is radius of cylinder, can be calculated by this formula, and M0 here, the moment of the duplet or intensity of the duplet, M0, and U, velocity of uniform flow. Okay, now we would like to find the velocity of the fluid flow at about r theta outside cylinder. That means r greater than capital R, small r greater than capital R. That means this point outside of the cylinder. So you can use the relationship between phi psi to the velocity UR and U theta. So you can find UR like this and U theta like this. So this formula allow you to calculate the velocity at a point outside of a cylinder. Now we would like to find the velocity on the surface of the cylinder. Now we just put r, small r equal capital R. So this one minus 1 is 0. Therefore we get the velocity UR equal 0 on the surface of cylinder. And this is small r equal capital R. This one 1 plus 1 is 2. Okay, 2. You put 2 here. U theta equal 2 U psi theta minus gamma over 2 by R. So we get the formula here. UR equal 0 and U theta like this. And now we find the stagnation point on the surface of cylinder. The stagnation point is the point at location that the velocity is 0. So you put this one 0 and this one 0. You find the stagnation point on the surface of the cylinder. So solve this equation. This one 0. So you can find theta equal arc sine of minus gamma over 2 pi r u. This one, and this is this equation you have to solve analytics for this solution. And for this solution, we get the solution if this one inside -1 +1, because psi any angle between the value of psi any angle between -1 and 1. Therefore, this one, this value have to smaller than 1. Now, if this one smaller than 1, that means gamma smaller than 4 by RE. In this case, we have the solution, and we have two solutions. We have two solutions. That means two destination point at A and B for this one. You can see this one, A and B. This is a destination point here and here, symmetric about y-axis for gamma less than 4 pi RE. We get the two solution, two destination point. And in the case if this one equal this one equal this one, we get this one 1. So in this case, we just one solution, and the destination point at just C. Okay. In this case, A move to C, B also move to C. So in this case, we get just one solution. That means one destination point when the condition satisfied, gamma equal 4 by RE, we get the one. But in the case, if this one greater than this one, then this one greater than 1. If greater than 1, this is no solution. Okay? If this one greater than this one, no solution find. That means we cannot find the destination point on the surface of the cylinder. Okay, but we can find the destination outside of the surface of cylinder at D here. In the case if R greater than 4 pi RE, so we get the destination point D here. And I give you the formula to calculate RD, the distance from O to D, RD here. Equal this, use this formula. And now we would like to find the pressure on the surface of cylinder. We use the Bernoulli equation between a point on the surface of cylinder and one at the infinity point. Infinity point. So we have delta B star equal B star minus B star infinity. But if B star infinity is zero, that means we use the gauge pressure, and pressure at the infinity point is 0. Therefore, we get the pressure on the surface of cylinder like this. This formula. So you can see this depend on theta and gamma as well. Okay. Now, after we have the pressure, we can find the force act on the cylinder surface by take the integral along the curves along the circuit. We take the integral. You this one and you take ds on the circuit. Multiply with this one, we get the small force. And after that, you take the integral over the circuit. You get the force. But in this case, we take two components of the total force. The component when we take projection on x, Sx we call Fd, the drag force. And if we take projection on y, Sx, we get the total force we call the lift force here. Fd, the drag force, is 0. After you take the integral, you get this one 0. But for the lift force, you take this one, and this one r sine theta multiplied by theta. That means ds, a small arc length on the surface of the circle. Okay, and after you take the integral from O to 2 that means along the closed curve circle, you get the value of FL is rho multiplied by U multiplied by gamma. And A here. And so now you can see this is called lift force, and Joukowsky theorem on the lifting force. Theorem, Joukowsky theorem. When the ideal fluid flow with velocity U flow around a body with a vortex intensity gamma, okay, a vortex intensity gamma will apply to such body a force with the direction normal to E. So you can see here, if this is U parallel to x-axis, then the force is normal to x. That means in the y direction. Normal to E. The direction is determined by rotating U a 90 degree angle in the opposite direction to gamma and having value equal to rho U gamma. That's the Joukowsky theorem. So you can see here, this is U. The direction of U parallel to x-axis, and the direction of FL, the lift force, by rotating U 90 degree, either this direction or either this direction, but opposite with gamma. Gamma like this, so we rotate U like this. So that means we get FR parallel and the same direction, the same orientation with Y. So we get FL like this, and this called the lift force. Have to act on the body, okay, remove the body from the gravity, have the body fly. So this is the Joukowsky theorem. You remember the velocity U1 and the intensity gamma. We have uniform flow and vortex intensity for ideal fluid, okay, U gamma. And then we can get the lift force equal this one, And rho here, the density of the fluid. Okay, you this one. And we prove here, this one. We come to the comment. The intensity of the leaf force is proportional to the density of fluid here. The density of fluid here. And the uniform flow here. And the intensity of free vortex gamma. That means the value of the leaf force increase if rho increase, U increase, or gamma increase. Okay? The intensity of the leaf force proportional to the intensity of rho, U, and gamma. Leaf force exists only when both uniform flow and free vortex exist. The value of FL exists, that means different from zero. If both U and gamma exist at the same time, if just have velocity U, not gamma, so this is become zero. If U0 just has gamma, then this one also zero. So just U different from zero and gamma different from zero, both different from zero, then this one different from zero. That means FL E6 only if U and gamma E6 at the same time. Okay. The phenomenon of this leaf force is observed in experiment named Manners phenomenon. We consider about the flying of object, especially a plane, airplane. Okay. Joukowsky theorem is not only true for body with a circular shape, not true for circular shape. That means can be applied for other shape, but also for any form of shape. This phenomenon is widely used in the engineering of line. Is the basic principle of aircraft, you know, aircraft. And many devices work with the interaction between the machine and the fluid. Okay. Now we come to the very important part B, leap and rug force. And I say you that. Okay. I say you that. In the final exam about the potential flow, the part A, you have no question on the part A for the potential flow, even computation or theoretical question. No, on part A. We just study for knowledge, forget knowledge only. But for part B, leap and rug force, you will have one computational question and one theoretical question. Two questions in the final exam here. So now we come to this one. Conception. We will study the force acting on body as it moves in the fluid, not considering the Archimedes force. and gravitational force. We not consider Archimedes force or gravitational force. Fluid may have fixed or free border, finite or infinite. Here we consider only the incompressible fluid. That means in this chapter we consider incompressible fluid. That means the fluid with rho density constant, even liquid or air, even air. We assume that is the incompressible fluid. That means rho constant. In principle, we can use the Euler equation system for the ideal fluid or Navier-Stokes equation for real fluids to results. However, solving this equation system is very difficult, even for case the body having simple shapes or laminar flows. Normally, we only need to find the global quantity such as force coefficient, such as we consider later CD, CF, and so on, and the inertial coefficient due to the fluid influence that can be determined through the experiment result. So in this chapter, normally we use the experimental method. We get the result, some result from the experiment. Okay, normally. When the incompressible real fluid moves through the body, or when the body moves in the fixed fluid, it's the same. There will exist two forces acting on the body force or the body surface. This is very important. You remember the force due to the pressure acting perpendicular to the surface. That means the normal component, the normal force, the normal to the area. If you take a small area dA on the area A surrounding the body, so the force acting on dA, normal to dA, one normal to dA component, and the force caused by the frictional force having the direction tangent to the surface. That means when we take a small dA on A surrounding the body, at dA we have two components. The first component normal to dA, due to the pressure, we call pressure, and the second component lies in dA, tangent with dA, that we call the friction force. So always we have two kinds, the pressure force acting normal to dA and the friction force acting in the same plane with the area dA. So you remember this one. We have two kinds, normal and friction force, pressure and friction force. Now the component of the total force project on direction perpendicular to the movement direction is called the lift force. Now you try to remember the definition of the lift force. The lift force is the component of the total force. The component of the total force of the fluid acting on the body. Total force, that means the total force by the fluid acting on the body. Now we take projection, we get component of the total force projected on the direction, but this direction not more to the moment direction is called the leap force. When integrating the part of the leap force on the force differential due to the stress acting on the differential surface area on the entire surface area, we will get the leap force. When we take the integral over the area A, we get the leap force. You remember the leap force not more to the direction of the velocity. That means when the body move, the force acting not more to the direction of the movement of the body. This kind we call leap force. Okay. Leap force is the sum of all the fluid dynamic force on a body not perpendicular not more to the direction of the external flow approaching that body. Okay. Leap force or lifting force or simply lift can also be defined as a mechanical force generated by solid object as it moves through a fluid. Similarly, the projection of the total force on the moment direction is called drag force. Now we come to the concept of the drag force. So the drag force not more to the leap force. The leap force not more to the direction of the body, but the drag force in the same direction with the movement of the body, the drag force. So we can projection of total force on the movement direction is called drag force. When interacting the resistance component of the force differential due to the stress acting on the differential surface area on over surrounding surface area, we will get the shape drag force. That means the drag force, but we call shape because the body is a shape kind, a kind of shape. We generally we call shape drag force. Drag, sometimes called resistance. That means when a body moves in the fluid will act on the moving body, a force resistance of the movement of the body. So we show here drag, sometimes called resistance, is a force that resists movement of a solid body through a fluid in the direction of its movement, in the same direction but opposite direction, opposite with the movement. Drag force can be also defined as the acting force of the fluid flow on an immersed body in the direction of the flow relative velocity. If the motion can produce weight on the incompressible fluid surface, the rug force due to the weight effect is called the weight resistance force. So this case you can read at our lecture note. Now we come to another important point. In the steady flow of ideal fluid, that means in this case, ideal fluid, that means mu equals 0, no friction force, mu equals 0, no viscosity, ideal fluid, no viscosity, only the pressure component exists. In this case, the force act on the area dA, small area dA, just normal to the area only, because this is ideal, no friction. So the rug force is 0. So therefore the rug force is 0. However, the leap force can occur in the movement of the ideal fluid when there is a combination between free vortex and uniform flow. This is we know. We just know on the chapter the portion concerning with the potential flow. Okay, free vortex and uniform flow. We just know as we have shown in the plane potential flow we just studied. In fact, circulation, the intensity of the vortex should be required to create leap force in both real fluid as well as the ideal fluid. Now we come to the rug force. When there is no way resistance force, we delete this one, we not consider this one, and the induced rug, delete. The overall resistance is a self-break force only, self-break force, which can be pressure or rug due to friction, or combination of both depending on the shape of body in motion. The rug force. The development and the separation of the boundary layer play an important role for the frictional resistance. For the body, backward weight reason can and also for the pressure distribution on the body surface, and therefore affect the pressure resistance. So this is very important. So you have to remember this one, because in the final exam we have a problem, and in this problem you use this formula to calculate or to solve the problem. Rug coefficient is defined as follows. So you can use this formula, or you multiply this term from the right to the left, and you get FD equal 1/2 rho U square A multiplied by CD. You get the formula. So in this case, we use the formula to calculate CD. CD is called rug coefficient, and used for experiment research. So CD is a function depend on shape of the body, okay, Reynolds number, Mach number, root number, friction coefficient of body surface, and free flow confusion. And here you know A, unit square meter, reference area, usually a frictional area, frontal area normal to the velocity. This is depend on the case. We study raw density of fluid, unit kilogram per cubic meter. the velocity in meter per second, and FD unit Newton. This is the rack force. Friction rack. That means the rack due to the friction force. Okay, rack due to the friction force. Poor friction rack occurs in the case of fluid movement parallel to the flat black surface. If we have a flat black surface and this is parallel to the movement, so the rack force just come from the friction only, so we call friction rack force. The average friction coefficient we call CF here. In this case, we not use CD, but we use CF. F for friction. In general, you can use CD instead CF. You can use, okay, or rack coefficient CD instead of this one. Depend on the condition of boundary, whether laminar or turbulent. That means depend on the Reynolds number. So this is give you a formula, calculate the Reynolds number. So you can pass this one. You just remember this one. And in the problem, the problem given you the value of CD. So you no need go to detail. Okay. And this is some formula from experiment. This is streamlined body, a kind of a body having the surface does not create the separation of the boundary laser. You can pass this one or this one. And pressure resistance. This is the second kind. The first kind the friction rack, and the second kind pressure resistance. That means the rack due to the pressure. Okay. Poor pressure resistance occur when placing a flat plate perpendicular to the moving direction. That means you have a flat plate here, and the movement direction here, normal to this area. So in this case, you get the pressure resistance, and this you get the rack force by the pressure, just pressure. In the second case, if you have the area like this, very thin and parallel to the flow, and the flow friction on two surfaces of the plane, we get the friction on rack. In this case, we get the pressure, okay, pressure rack by the pressure. When the friction force is perpendicular to the direction of movement, it does not create a friction on resistance component. It only affects boundary, layer thickness, and pressure distribution on flat sheet surface. It is just the condition of the real fluid having friction that makes flow separate the boundary layer at the back of the flat plate, creating a large pressure difference between the two flat plates. You see here, if the flow normal to the area, we get the pressure here. And this is the distribution of the pressure. Maximum at the center, maximum. And zero at both outside, okay, here. And you know, here we have some this is we get the pressure at a negative value here. So the distribution of the pressure at backside of this black is like this. Okay, like this. So now we sum this one from left to right, and this one because of negative, that means also from left to right. You you sum this one and this one, you get the total force, pressure force act on this black. So you can see a formula to describe the value of CB. B here for pressure, B for pressure. Okay. When we have a rectangular flat black with the height B and the length L, so we can find CD depend on the number of Reynolds B. Reynolds B, that means the Reynolds computed by B. That means Reynolds B equal V multiplied by B divided by N. And the geometry, that means the ratio between B and L, the height and the length L. So if Reynolds B greater than 1000, and if B over L, here you can see this curve, so the value of CD, the value depend on the ratio between B and L. If B and L between O dot 2 to 1, so the value of the rack CD equal 1.16. CD 1.16 if B over L between this one. But in this case, if this one is a circular flat black, when Reynolds number RD, that means Reynolds calculate by diameter D equal V multiply D over N, greater than 1000, then we get the rack coefficient CD equal 1.12. And here you see the flow from upper to lower. That means in the direction of vertical and downward. If the flow direction like this, then this is the shape. We have many shapes, and we have the value of CD like this. Remember the flow direction downward. Okay. So we pass the time. So maybe you read carefully at home about the rack. So here the experiment give you so many value of CD depend on the shape, and this is another phenomenon, and this is another permanent. And for leap fork, okay. So maybe we stop here, and we have one more class. At the next week we have one more class. So we try to finish the leap fork, and about the airplane. Okay, airplane here, just a little bit.